Hi everyone, I am Tibia Viknaraja. Today I am going to present about IEEE wireless LAN standards and networking technologies. We move into IEEE Econ 2.11 standards overview. This slide provides an overview of an evolution of IEEE Econ 2.11 Wi-Fi standards. We began with Econ 2.11b Wi-Fi 1 operating at 2.4 GHz with 11 Mbps, which laid the foundation for wireless connectivity. Econ 2.11a Wi-Fi 2 introduced the 5 GHz band, boosting speeds up to 54 Mbps through it lacked backward compatibility. Econ 2.11g Wi-Fi 3 combined the 54 Mbps speed with the 2.4 GHz band, maintaining compatibility. A significant leap occurred with Econ 2.11n Wi-Fi 4 supporting both 2.4 or 5 GHz and achieving up to 600 Mbps through MIMO technology. Econ 2.11 AC Wi-Fi 5 focused on the 5 GHz bands, pushing speeds to 6.9 Gbps with MU-MIMO and wider channels for higher bandwidth applications. The current widely adopted standard Econ 2.AX Wi-Fi 6 operates across 2.4 or 5 or 6 GHz, offering up to 9.6 Gbps. It's designed for high density environments, improving efficiency with OFDMA and BSS coloring. Looking at Econ 2.11b Wi-Fi 7 is emerging promising even after speeds of up to 46 Gbps across all three bands, aiming extremely high throughput and low latency for future applications. Next, we move into frequency bands and characteristics. This slide examines the characteristic of different wireless frequency band. The 2.4 GHz band offers better range and volt penetration, but is prone to interference and congestion due to shared use with devices like Bluetooth and microwave ovens. This often leads to slower, less reliable connections. In contrast, the 5 GHz and 6 GHz bands provide high speeds and less congestion due to more available channels. However, their traits of shorter range and difficulty penetrating volts, potentially requiring more access points for coverage. A crucial concept is channel bandwidth. Wider channels such as 160 MHz significantly increase data throughput and performance, which modern Wi-Fi standards leverage for their impressive speeds. Next, wireless security standards. This slide traces the evolution of wireless security standard WEP, Wired Equivalent Privacy. The initial standard used RC4 and static keys but was quickly found to be highly vulnerable to attacks, rendering it ineffective. WPA, Wi-Fi Protected Access, emerged as an interim solution, introducing TKIP and dynamic key, which provided better security than WEP by changing encryption keys. Frequently, the major advancement came with WPA2 based on IEEE Econ 2.11i, which adopted robust AES encryption and CCMP. This made WPA2 much stronger and established it as the industry standard for many years. The latest standard, WPA3, introduced in 2018, further enhances security with SAE, simultaneous authentication of equals authentication, protecting against password guessing and offline dictionary attacks. It also incorporates forward secrecy, ensuring past communications remain secure even if keys are compromised. WPA3 represents the latest and more secure standard, offering enhanced privacy and resilience. Next, security theories and mechanisms. This slide highlights fundamental security theories and mechanisms vital for protecting wireless communication. Authentication, specifically reference IEEE Econ 2.1x, is port-based network access control network. It uses authentication servers like Radius to verify user credentials before granting network access, preventing unauthorized entry. Encryption is the process of converting plain text to ciphertext to prevent unauthorized reading of data during transmission. This ensures confidentiality, making intercepted data unreadable without the correct key. Finally, integrity current is that data has not been altered during transmission. This is often achieved using message integrity checks. which detects any tampering. Together, these three pillars form the cornerstone of secure wireless technology. Next, Bluetooth technology. This slide introduces Bluetooth technology for short-range wireless communication in personal area networks. Its a key feature include frequency hopping spread spectrum, which reduces interference by rapidly switching frequencies, and Bluetooth low energy. Designed for ultra-low power consumption in IoT devices, Bluetooth supports both point-to-point and mesh networking. We compare its various classic Bluetooth 10 to 100 meter range high power is ideal for audio streaming and file transfer. Bluetooth low energy 10 to 240 meter range low power is widely used for wearable and IoT devices. Bluetooth mesh extends BLE's capabilities, allowing devices to form a mesh networks for increased range 100 meter plus, and is particularly useful for smart home applications. Next, Zigbee technology. This slide focuses on Zigbee technology for low power, low data rate wireless mesh networking, primarily for IoT and home automation. Based on IEEE 2.15.4, Zigbee is highly scalable, supporting up to 65,000 nodes and low power consumption, allowing device batteries for last 4 years. Applications are diverse: smart home control for lighting, thermostat and security, industrial control for equipment monitoring and automation, health monitoring through remote patient devices and utility metering, and smart gas, water and electricity meters. Zigbee is robust and energy efficient solution for interconnected IoT ecosystem. Next, Li-Fi light fidelity technology. This slide introduces Li-Fi or light fidelity, and innovative wireless communication technology utilizing visible light, infrared or ultraviolet spectrum. Unlike Wi-Fi, Li-Fi modulates light from LEDs to transmit data. Li-Fi offers several compelling advantages: much high bandwidth than radio waves, leading to faster speeds, inherent security because light cannot penetrate walls, preventing external interceptions, and no electromagnetic interference, making it exceeding 10 Gbps, positioning it as promising technology for future data intensive applications. Next, LoRa long range technology. This slide details LoRa, a long range low power wireless technology designed for IoT application. It operates using surf spread spectrum CSS modulation, which spreads a narrow band signal over a wider signal, enabling communication over very long distances and low power requirements crucial for battery operated sensors. Key parameters include operation in sub-gigahertz frequency bands, example 868 or 915 MHz. Variables: spreading factors SF7, SF12 for range data rate trades-off, and various bandwidths 125, 250, 500 kHz. LoRa is well suited for smart agriculture, soil monitoring, asset tracking, GPS, less location, environmental monitoring, weather station, and utility management, remote meter reading. Next, LoRaWAN protocol. Building on LoRa, this slide introduces LoRaWAN, a MAC layer protocol that manages communication between gateways and nodes, handling security and data rates for wide area IoT networks. Its features include adaptive data rate, which optimizes data rates and power for devices, AES 128 encryption for end-to-end security, and defined device classes ABC, balancing battery life and latency. LoRaWAN is a cornerstone for smart city applications such as automated smart lighting control, smart parking system providing real-time availability, environmental monitoring for air quality, industrial IoT for equipment maintenance, and utility metering for efficient resource tracking. Next, RFID and NFC technologies. This slide comprises RFID, radio frequency identification, and NFC, near field communication. Near field communication. RFID uses electromagnetic fields to identify and track tags operating across LF, HF, and UHF frequencies with ranges from centimeters to meters. It's widely applied in inventory and supply chain tracking and access control. NFC is subset of RFID, specifically operating at HF 13.56 MHz for secure, very short range, less than 10 cm communication. This close proximity enhances security. NFC is commonly used for contactless payments. Example, Apple Pay. Digital business cards and device pairing, simplifying secure interactions. Next, we move into IoT and wireless sensor networks. This slide distinguishes between broader IoT and wireless sensor networks. IoT encompasses physical object with sensors, software, and connectivity that exchange data over the internet, utilizing technologies like Wi-Fi, cellular, and LoRa. Its applications span smart homes, wearable, and smart factories. WSN consists of spatially distributed autonomous sensors that monitor physical or environmental conditions. Key parameters include node density, network topology, star or mesh, and energy efficiency, crucial for battery-powered sensors. WSN applications include fire detection, structural monitoring, and surveillance. Essentially, WSNs are foundational component and a specific type of IoT deployment focused on environmental data collection. Next, body area networks, BAN or WBAN. This slide introduces body area networks, also known as wireless body area networks, which involves low power sensors placed on, in, or around the human body for continuous health monitoring and data collection. The IEEE 2.15.6 standard governs these networks, emphasizing low power consumption, high reliability, and critical data security and privacy. Applications include ECG monitors for cardiac health, glucose sensors for diabetics management, temperature patches for fever detection, accelerometers for fall detection and activity tracking, pressure sensors for wound healing, and smart prosthetics for enhanced mobility. Bands are transforming healthcare through proactive health management and remote patient monitoring. Next, vehicle area network, VANET. This slide discusses vehicle area network is a critical technology for intelligent transportation. VANET involve vehicle and roadside units acting as network nodes to provide safety and information services, encompassing V2V, vehicle to vehicle, and V2I, vehicle to infrastructure communication, collectively known as V2X, which means vehicle to everything. Technical parameters include DSRC, dedicated short range communications for high speed, low latency communication, high mobility support, and real-time data exchange. Key applications are collision avoidance, real-time traffic updates, autonomous coordination, example platooning, and emergency response. VANETs, which means vehicle area networks, are instrumental in creating safer, more efficient and intelligent transportation system. Thank you.